So if you watch a robot, perfectly chop a vegetable on YouTube, or execute this flawless backflip.
Right, those viral videos.
Yeah, exactly. What you aren't seeing in those videos is the human engineer just off camera. Like the person holding a cold slice of pizza, ready to hit the emergency stop button for the, I don't know, 500th time today.
Oh, absolutely. The glossy, edited videos, they never show the grueling reality behind the lens.
No, they definitely don't. They don't show the team of exhausted researchers physically picking up the robot, placing it back on its starting mark, and tweaking a single line of code every single time it drops a coffee mug or misjudges a jump.
Yeah, that illusion of autonomy is really hiding a massive amount of manual human labor. We are essentially, well, we're acting as the permanent training wheels for these machines.
Right.
Because every time a physical robot learns a new skill, there's a human babysitter required to facilitate that learning loop.
Okay, let's unpack this, because today we are jumping into a deep dive on a stack of research that suggests those training wheels are, well, they're finally coming off.
It's a huge deal.
It really is. We're looking at a state-of-the-art framework called ENPIRE, and this was developed by researchers at NVIDIA, Carnegie Mellon, and UC Berkeley. And for you listening, their mission here is pretty staggering.
It really changes everything.
Yeah, they're demonstrating how AI coding agents can now autonomously train physical robots in the real world. So no humans babysitting the reset button. No humans carrying the robot back to the starting line.
Right, and it represents a massive paradigm shift in how we approach physical intelligence. Like, if you look at the core thesis from our GenAI Foundation's source material, it argues that to achieve true adaptable robotics, we need a repeatable automated feedback loop in the real world.
And ENPIRE provides that missing abstraction.
Exactly.
It makes me think of a toddler learning to walk. Right now, the state of robotics is kind of like a toddler who stumbles, falls, and then just lies there on the floor waiting for a parent to manually pick them up.
Yeah, to place their feet flat and point them in the right direction.
Exactly, to point them where they need to go to try again. Like, they can't learn from the fall until the parent resets the environment. So ENPIRE is basically giving that toddler the ability to realize they fell, pick themselves up, figure out what went wrong, and try a new strategy entirely on their own.
And that autonomy to fail and reset is the holy grail here. But, to understand why ENPIRE is such a breakthrough, we have to look at where current AI agents have been hitting a brick wall. We really have to talk about the simulation trap.
Right, because we already have brilliant coding agents out there. We're talking about models like Codex, Quad Code, Kimi Code.
Unbelievably smart systems.
Yeah, they really are. These AI models can write complex algorithms and solve incredibly dense tasks in digital simulators. Like, in a virtual digital world, they look like absolute geniuses.
But, and this is the big but, the moment you take their code and upload it into a physical robot arm sitting in a real room, they suddenly look, well, completely incompetent.
It's so wild to me.
Yeah, and that failure comes down to the fundamental difference between a digital simulator and physical reality. In our source material, the researchers detail an experiment using something called the push-T task.
All right, so for you listening, the push-T task sounds deceptively simple. The robot just has to slide a T-shaped block across a table into a specific target zone.
Yeah, just pushing it.
Right. It's what roboticists call non-prehensile movement, meaning, the robot isn't using fingers to grab and lift the block. It just has to push it along the surface.
And in simulation, all three of those coding agents, so Codex, Claude, and Kimi, they totally nailed it. They used heuristic learning.
Which basically means they wrote a set of rule-based guesses, right?
Yeah, exactly. They tested them in the simulator, successfully generated the code, and aligned the block. The math worked out perfectly. But then the researchers took those exact same agents with those exact same successful strategies and moved them to control physical hardware in the real world.
And it all fell apart.
Oh, completely. The results plummeted. 2 of the 3 agents failed entirely.
Wow. They just broke down. Like, the task was exactly the same, but the medium changed.
What's fascinating here is why the physical world breaks them. A simulator operates on perfectly predictable math. Like, if you tell a simulator to apply a specific amount of force to an object with a specific mass, that object will move exactly X millimeters.
Every single time.
Exactly 1,000,000 times out of 1,000,000. The real world, however, has time-varying and non-deterministic physics.
Meaning the physics just, change from second to second in ways you can't really predict.
Right. I mean, the friction on the table might be slightly different on the left side than the right side just because someone wiped it with a cloth yesterday.
Oh, wow.
Yeah, or the camera sensor might have a tiny speck of dust on it, introducing visual noise. Even the actual motors inside the robot arm get warmer as they run, and a warm motor responds to electrical currents slightly differently than a cold motor.
That's crazy to think about.
Yeah, the physical world just isn't a perfect equation. It's messy, it's noisy, and it's chaotic.
Wait, so if the real world is that messy and unpredictable, how does an AI agent even know it made a mistake? Like, if the block slips halfway to the target because of table friction, wouldn't the AI might think it succeeded just because it finished executing its lines of code?
That is the exact problem.
Right, because it doesn't inherently know the block didn't reach the target. So without a human walking over, looking at the block and hitting a button that says, nope, try again, the AI is essentially blind to its own failure.
And solving that blindness is the entire purpose of the first stage of ENPIRE. So ENPIRE is an acronym, and the EN stands for Environment Construction.
Okay.
Before the robot ever attempts to learn the task, the coding agent builds an automated, immutable sandbox.
See, this is where the research starts sounding a bit like science fiction to me. The AI is building its own playground rules before it even starts playing.
It really is, and it uses a tiny amount of human feedback to do this. We're talking about just a few minutes of video showing what a successful task looks like and what a failed task looks like.
That's it. Just a few minutes.
Just a few minutes. And from that tiny seed of visual data, the coding agent writes its own strict APIs for the robot.
Okay, let me pause on APIs for a second, just to make sure we're on the same page here. An API, an application programming interface, is basically a menu of commands. So instead of the AI having raw, chaotic control over every single electrical voltage in the robot, it creates a neat little menu of actions it's allowed to take, like, move left, move right, close grip.
Exactly. It sets up the boundaries, and more importantly, it literally writes its own visual reward functions. It writes the software to judge its own success or failure.
Yeah, there's a specific detail in the research regarding this that really stood out to me. The researchers gave the system a zip tie cutting task. So the robot has to pick up a pair of scissors, maneuver them over a plastic zip tie, and snip the tail off.
Which is a highly precise, highly visually complex task.
Right. And to figure out if it actually succeeded in cutting the zip tie, the agent didn't just look for a generic change in the pixels on a camera. It proactively designed a complex reward function using two different camera views.
Yeah, one top-down view from the ceiling and one wrist-mounted view right on the robot arm.
Exactly. It wrote the code to crop the images and then use object segmentation. And for anyone listening who is unfamiliar, object segmentation is like when you use the magic wand tool in Photoshop to isolate a specific item.
That's a great way to describe it.
Yeah, so the AI wrote code to highlight just the zip tie, ignoring the table and the scissors, and then ran a geometric check on the shape of that highlight to see if the tail was actually severed.
And the craziest part, the agent optimized this visual check to run in under 150 milliseconds.
Which is, that's approaching the reaction speed of the human eye. It's making these microscopic visual judgments in real time, constantly checking its own work without a human ever watching a monitor.
And because it can judge its own success or failure instantly, it can also reset itself instantly. When it fails, it doesn't just flail around or flash a red light waiting for an engineer.
Right.
It triggers an automated reset routine. But, and this is key, it's not just returning to square one.
Yeah, it resets to what they call the precision bottleneck. So if the task is inserting a tiny metal pin into a motherboard, and the robot drops the pin at the very last millimeter, it doesn't start the whole sequence over by searching the table for a new pin, picking it up, and driving over to the board.
That would just be a waste of time.
Exactly. It resets the robot to hover right over the hole, already holding the pin, ready to try the absolute hardest part of the task again.
It isolates the exact moment of failure and drills it repetitively. Just like a musician practicing the one hard measure of a song.
Now, my initial thought when reading this was about safety. Having an AI writing its own code, testing it in the real world, failing, and instantly resetting itself at high speeds, it sounds like bowling without the bumper rails.
Oh, for sure.
Like if it makes a bad calculation, couldn't it just smash the robotic arm straight through the table? Hardware isn't cheap.
That is a huge concern, which is why safety constraints are built directly into the environment construction stage. The agents aren't given raw, unconstrained power. The environment restricts the physical configuration space, so the bumper rails are firmly up. But beyond just software limits, there are mechanical safeguards too, like the torque-limiting compliant grasp on their 1 degree of freedom gripper.
Okay, let me see if I have this right. A 1 degree of freedom gripper is basically a simple claw. It just opens and closes one movement, and torque-limiting compliant grasp. So instead of telling the robot, close your hand exactly 2 inches no matter what, we're telling it, close your hand until you feel a certain amount of physical resistance.
You've got the exact mechanism. See, the traditional brute force approach to robotics is rigid positioning. You tell the motor to go to a specific coordinate.
Right.
If a delicate motherboard is in the way, the motor will just push harder and harder to reach its coordinate until the motor burns out or the motherboard literally snaps in half.
Yikes.
Yeah, but with torque limiting, the command bounds the grip force directly.
So if the robot misaligns its claw on a delicate piece of hardware, instead of pushing through and snapping the board, it feels the resistance and safely stalls out.
Exactly. The environment reads that motor stall as a failure. The AI registers a score of 0 for that attempt, and it automatically triggers the reset. No broken parts, no human intervention required.
It creates a physical boundary that mirrors a digital error code. That is so clever. So the sandbox is built, the safety rails are up, the AI can judge itself and reset itself. Now that it can safely fail, how does it actually learn from those failures?
This brings us to stage 2 of the framework, which is the PIRE in ENPIRE, policy improvement and evolution.
Okay, and this is where the robots are truly unleashed. The coding agent accesses a baseline training code base and just starts acting like a lead research scientist.
It formulates hypotheses, tests out different machine learning algorithms, and runs them on the physical robot to see what actually works. Yeah, so the agent might decide to test behavior cloning, where it tries to mimic successful human demonstrations by mapping visual inputs directly to motor actions. Or it might pivot to reinforcement learning, where it relies on trial and error, constantly tweaking its movements to maximize that reward score we talked about earlier.
So the agent is looking at real-world data, checking the error logs, seeing that, a specific wrist rotation caused the pin to drop, and then jumping back into the Python code to tweak the parameters. It is an end-to-end autonomous research lab.
It really is. And the researchers didn't just do this with one robot in isolation. They deployed a multi-agent scaling system,
Right.
a synchronized robot fleet.
Here's where it gets really interesting. They set up 8 bimanual 6-DoF YAM robots.
Right.
And YAM stands for yet another manipulator. And for context, bimanual means it has 2 arms, and 6 degrees of freedom means each of those arms can move in 3D space just like a human arm. So it has a shoulder, an elbow, and a wrist that can pitch, yaw, and roll.
Super complex machinery.
Yeah, so you have 8 of these complex 2-armed robots, all operating in the same room at the exact same time.
And each of those 8 physical robots is controlled by its own distinct AI coding agent. You have 8 AIs running 8 physical machines, but they aren't isolated. They are coordinating entirely through Git.
Wait, Git, like the version control system that human software developers use to collaborate, they are running a 247 autonomous hackathon.
Exactly. Think of Git in this context as a massive shared Google Doc for robotic muscle memory. Agent A might be testing an online reinforcement learning approach on Robot 1. Agent B is trying a hybrid behavior cloning approach on Robot 2.
Okay.
And they are independently pushing their code updates to the main branch, monitoring their peers' branches, and analyzing the success rates of the other robots in real time.
So if Agent C notices that Agent A's code is suddenly getting like a 90% success rate, while its own code is stuck at a 40% success rate, Agent C doesn't just keep banging its head against the wall.
Not at all.
It literally executes a Git pull. It downloads the successful training recipe from its peer, abandons its own failing hypothesis, and starts building on top of the winner's code.
Exactly. And when we talk about an AI reading a pull request in this scenario, it is looking at the specific hyperparameters its peer changed.
And hyperparameters are essentially the tuning knobs of an AI model. Right.
Right. Things like how fast the robot is allowed to move or how heavily it weighs a certain visual input. The failing agent sees which knobs the successful agent turned, adopts those settings, and continues the experiment. The acceleration this provides is just staggering.
I mean, the source material highlights a pin insertion task to prove this.
Right.
The robots had to plug tiny metal pins into 4-millimeter diameter holes. When they ran this experiment with just one agent controlling one robot, it took over an hour and a half of physical wall clock time to reach a near-perfect success rate.
Which, to be fair, is already incredibly fast for a real-world fine motor task.
It totally is. But when they scaled it to the 8-agent fleet, With all of them coordinating and stealing each other's successful code through Git, they reduced that time to just 40 minutes.
They cut the learning time by more than half. And they also applied this fleet approach to a GPU insertion task.
Oh man. Seating a highly expensive GPU chip perfectly into a thin motherboard socket. Just thinking about a robot trying to jam a graphics card into a motherboard gives me anxiety.
I know, right? But in that multi-agent setup, the coding agents realized that if they just learned to insert the GPU from one specific angle, the policy would be fragile.
Right.
Like if the motherboard was shifted even a millimeter, the robot would fail. So the agents autonomously used code-based policies to apply something called domain randomization.
Domain randomization is basically intentionally messing up the environment to make the AI robust.
That's it exactly. During the automated reset phase, the AI actively altered the starting position, the angle, and the height of the GPU in the robot's grip. Yeah, it deliberately made the task harder on itself, forcing the neural network to learn how to handle endless variations of the approach. The final skill became virtually bulletproof.
So they are acting as their own strict teachers. And this knowledge doesn't just disappear when you turn the robot off either. The research introduces this concept of agentic continual learning.
The knowledge absolutely transfers between entirely different tasks. When the fleet of agents finishes mastering the pin insertion task, they don't just stop. The agents actually write up markdown summaries.
Like highly detailed text documents.
Yes, almost like a scientific abstract. They document exactly what hyperparameters worked, what approaches failed, and what insights they gained about fine motor alignment.
So they're writing their own technical documentation. That is insane.
Yeah, and when a completely new task begins, like the GPU insertion, that markdown summary is handed to the coding agents on day one. They read the text, integrate the findings into their new code, and it gives them a massive head start.
So they don't have to relearn the basic physics of aligning a peg with a slot.
Right, they just adapt that pre-existing knowledge to the new, wider shape of the GPU.
Okay, let me play devil's advocate for a minute here.
Yeah.
We're talking about fleets of complex robots.
Right.
We have multiple cutting-edge large language models constantly generating code, analyzing video feeds, pushing to Git, writing markdown files.
Right.
So is the solution to robotics just to throw a massive army of robots and infinite cloud computing power at a problem? Like, what is the catch here? This has to be incredibly resource intensive.
That's a great question, and you've hit on the exact limitation the researchers themselves spent a lot of time analyzing. It really comes down to the economics of robot learning.
Yeah.
To actually quantify this bottleneck, the ENPIRE framework introduces two new metrics to benchmark autonomous research. The first is MRU, or mean robot utilization.
Which is just the fraction of time the physical robot arm is actually moving and practicing the task.
Exactly. And the second metric is MTU, mean token utilization. This measures how many LLM tokens the coding agent is consuming per minute.
Essentially, how much computing power the AI's brain is costing to run while it figures out the code.
Spot on. And the catch they discovered is really fascinating. As you scale the fleet from 1 agent to 8 agents, the MRU, the physical robot utilization, actually decreases per robot.
Wait, if there are 8 robots instead of 1, shouldn't they be doing more physical practice, not less?
You would assume so, but remember the coordination required. With 8 agents constantly generating new data and pushing code, there are way more error logs to read, way more peer branches to summarize, and way more complex code to debug.
Oh, say.
So the physical robot arms actually end up sitting completely idle for longer stretches of time while the coding agents are, thinking.
That's so funny to picture. The physical robots are just sitting there frozen while the AI researchers are in a virtual conference room arguing over Git commits, reading each other's documentation.
Yeah, exactly. And while the robots sit idle, the MTU, the token consumption, is skyrocketing. The researchers found that the token cost grows super linearly. So the total token budget you need to pay for to get a successful policy spikes aggressively when you use an 8-agent fleet compared to just a single agent.
So it's a massive economic trade-off. You are trading token efficiency, meaning you're spending way more money on cloud compute and API calls to the LLM in order to get a faster wall clock time in the physical world.
Right. And if we connect this to the bigger picture, this metric tells us exactly where the bottlenecks in robotics are shifting. Historically, the absolute most expensive part of robotics was the human engineer's time.
Designing the code, hitting the reset button, diagnosing the failure.
Yes. But now, ENPIRE proves we can eliminate that human time entirely, but we are paying for it in LLM tokens.
But as the cost of compute and tokens continues to plummet year over year, this multi-agent scaling is going to become the default, most economically viable way to solve physical tasks.
It is inevitable. The human bottleneck is finally being removed from the loop.
So what does this all mean for you listening? Whether you are working in tech, manufacturing, logistics, or you're just someone curious about where artificial intelligence is heading, the takeaway is massive.
Huge.
For decades, the bottleneck of human engineering has kept robots out of our messy, unpredictable lives. We had to build perfect, rigid factories around the robots because the robots couldn't adapt to our chaotic world.
But ENPIRE proves that AI is now capable of acting as its own robotics research scientist. It can write its own code, design its own safety tests, safely execute them in the messy physics of reality, and literally collaborate with itself to overcome its own failures.
And it's not just writing rigid, procedural code either. The research showed amazing synergy with neural networks. ENPIRE actually taught a vision language action model, specifically NVIDIA's GR0T model.
Which is an incredible model.
Yeah, it's a neural network that processes visual sight and text commands to output physical movement. ENPIRE taught it to perfectly hover above an object before grasping it. It proved that you can seamlessly weave together hard-coded procedural tools and deep, adaptable neural networks to get the absolute best of both worlds.
It creates a system that is both highly reactive to immediate physical changes and highly reasoned in its long-term strategy.
Mind-blowing.
It really is. But, looking at how fast this is moving, it raises a rather provocative question to end on.
Okay, let's hear it.
Right now, we have AI coding agents that can autonomously write software to adapt to the physical limitations of the world. They can tweak the code to handle slippery surfaces or heavy objects. But how long until they hit a wall where a software update just isn't enough?
What do you mean?
Well, how long until an AI agent analyzes its own hardware logs, realizes that its simple 1 degree of freedom claw is the actual physical bottleneck, and autonomously opens a CAD program to design a brand new 3 degree of freedom physical hand?
Oh, wow.
It could just send that file to a 3D printer and simply ask a human lab assistant to screw the new part onto its wrist.
We'll leave you to think about that. Thanks for joining us on this deep dive.